Dear guests of the first International Conference on Micromachines and Applications, I would like to welcome you to my presentation. My name is Anna Sękowska-Namiotko and I am a PhD student at Gdańsk University of Technology in Poland. I would like to present the results of my research in the presentation entitled Fiber Optic Sensor for Detecting Neoplastic Lesions in Biological Tissues, a Preliminary Study. The aim of my research was to develop an optical sensor to detect pathological changes in tissue, especially when they are surrounded by healthy tissues. This sensor will have the ability to differentiate between healthy and cancerous tissue based on the changes in its optical properties, which are visible in the interference spectra. This slide presents an abstract which I submitted to the first International Conference on Micromachines and Applications. When cancer spreads in tissues, it causes anatomical and functional changes. This affects how the light propagates in the tissue, therefore modifying the optical properties of biological tissue, such as refractive index, scattering, and absorption coefficient. Based on this information, I came up with a thesis that it might be possible to differentiate normal tissues from neoplastic lesions based on the changes in interference spectra. To achieve the goal of my research and verify this thesis, we have designed and developed a micromechanical system with a fiber optic sensor for detecting changes in the refractive index of biological tissues. In the research presented in my presentation, I decided to focus on liver tissues, as liver cancer survival remains relatively low considering the recent cancer treatment advances. This slide presents a list of refractive indices of healthy liver tissues and liver metastases. In a study by Giannus et al. Published in 2016, the refractive index of liver tissues was examined. Researchers examined the properties of tissue specimens from patients who underwent surgery. First group of samples came from patients without any liver disease. Results are presented in the first row. The second group of samples were excised from the liver of patients with liver metastases. Both non-cancerous and metastatic samples were examined, and those results are presented in second and third row. The measurements obtained in this study were performed using the low-coherence interferometry method. The constructed optical system uses a fiber optic sensor operating on the basis of a Fabry-Perot interferometer working in reflective mode with a silver mirror acting as a reflective layer and a cavity length of 150 micrometers. Further elements of the measurement setup are an optical spectrum analyzer, a broadband light source with a central wavelength of 1550 nanometers, and a single-mode coupler. The standard telecommunication single-mode optical fibers from Thorlabs were used to connect all components of the setup. This slide presents the layout of the measurement setup. In the study, I examined the interference spectra of two reference oils. One of them had the same refractive index as healthy liver tissues, the other represented liver metastases. Interference spectra of both reference oils were measured 10 times. In the measured interference spectra, 4 parameters were examined: the position of the central peak, signal intensity of the central peak, the visibility, and absorption. This slide presents the method of measurement of the central peak position and its signal intensity. Visibility is calculated using the formula presented on the slide, where Imax is the maximum intensity of the measured signal and Imin is the minimum intensity of the measured signal. Those parameters are presented in the figure. Absorption is visible on the interference spectrum as an increase in the position of the peak minimums. Therefore, it is proportional to minimum intensity of the measured signal Imin. This slide presents the set of 10 interference spectra measurements taken for reference oil characterized by refractive index 1.34. This is the same refractive index which characterizes liver metastases. This slide presents the set of 10 interference spectra measurements taken for reference oil with refractive index 1.36. It was clearly visible on the previous slides that the measurements taken for each of the reference oils in one set of 10 were almost identical. That is why I calculated the mean interference spectra for each of the oils to compare them in one figure. They are clearly different, and on the next slide we will compare the parameters examined for each spectrum. Refractive index 1.36 was the refractive index of healthy liver tissues, and the refractive index 1.34 characterized liver tissue metastases. It is clear that we observe the shift of central peak position for the reference oils representing tissue metastases, but we can also see differences in signal intensity of the central peak, visibility, and absorption. On the previous slides, it was clear that there are visible differences between obtained interference spectra for examined reference oils. We can see that developed setup is sensitive to the changes of refractive index as well as absorption. Based on the presented research results, we can draw a few conclusions. First of all, the interference spectra can be used as a source of information about changes in optical parameters of the tested biological material. Secondly, the developed fiber optic sensor is able to detect changes in the refractive index based on the changes in the shape of the interference spectrum. We can observe changes of signal intensity, shift in the position of central peak, and change of distance between peaks in the spectrum. Consequently, the developed measurement method will be used to distinguish between healthy and neoplastic tissues. There is a need for further research on biological tissues to fine-tune the developed method. Finally, the developed method will be used to design and produce a micromachine that can be used in biomedical applications. This slide presents the list of references. This research received financial support from the Technetium Talent Management Grant Excellence Initiative Research University program. I would like to thank you for listening to my presentation. I hope you enjoyed it. If you have any questions concerning my research, please don't hesitate to contact me via email. My email address is presented on the slide. Thank you very much, enjoy the rest of the conference, and goodbye.